Today's lecture we'll do chapter 6, which is about operational amplifiers. Let us begin by looking at this interesting circuit which is key to understanding operational amplifiers. So there is a voltage source Vs, there is a resistance Ri, R1, R2, and there is a dependent voltage source whose value depends on this voltage Vi across Ri. We want to analyze this circuit, but before we do, we'll just redraw this. So this is the same circuit, just drawn differently. This is kind of more easy to look at. So you see that it is the same, right? So you have Vs, Ri, Vs and Ri, and the voltage across Ri is Vi with the positive terminal connected to Vs. And at the other end of Ri, there is R1 to ground and R2 going to the dependent source. Alright, so there are 3 nodes plus ground. 2 node voltages are known, only one unknown voltage. So we write one nodal equation here, and we write for the voltages, this is of course Vs. This voltage is Vo equal to AVI, where A is a constant and Vi is this voltage. So Vi is Vs minus Va. So these are the equations and you can solve them. So I would like you to pause the video and solve for Va and Vo. So find Va and find Vo. The equations are all, in fact there are 2 equations and 2 unknowns, Va and Vo. So pause and solve. Okay, I will continue. Actually, I am not going to solve this. So I have written the equation here again and the circuit here again. I am focusing on that second equation, Vo is equal to AVI. So Vo is equal to AVI is equal to AVs minus Va. So we can rewrite this as Vs minus Va equal to Vo over A. We take the A on the other side. Now let us consider the case where A, the voltage gain is very large. It's tending to infinity, basically very large. So if A is very large, or as A becomes larger and larger, Vo over A tends to 0. Alright, if Vo over A tends to 0, that means Vs minus Va tends to 0. And then Vs is approximately equal to Va. If Vs is approximately equal to Va, then we look at this equation. This term goes away and we get only Va and Vo, and this is very easily solved. So we'll get Vo equal to 1 plus R2 by R1 Vs. Okay. With this background, let us look at operational amplifiers. Okay. So an operational amplifier, generally it's called an opamp, is an almost ideal voltage amplifier which has 2 inputs, 1 output, sometimes it has 2 outputs. It has a very high voltage gain. Amplifier amplifies voltages, so it has a voltage gain, and an opamp has a very large voltage gain, about 10,000 to a million. If we look into these 2 input terminals and find the Thevenin's resistance looking into these 2 input terminals, it is called the input resistance Rin, and that resistance is very large for an op-amp. It varies depending on which op-amp you are looking at, from about 1 mega ohm to about 1 tera ohm. Tera is 10 raised to 12. If we look into the output terminal, so if it has 1 output terminal, that output is measured with respect to ground. So if you look into the output terminals, this terminal and ground, and find the Thevenin's resistance, it is called Rout, and it is very small, in the range of 10 to 50 ohms, which for electronic circuits is very small because generally electronic circuit resistances are in the kilo ohms. Alright, this is the symbol for an operational amplifier. It's a triangle with 2 inputs, plus and minus, and 1 output. So we'll look at only a single output op-amp in this course. 2 output op-amp is kind of an advanced level circuit. The inputs, I will call these inputs applied to the positive and negative terminals as V plus and V minus most of the time. And so the op-amp has the output equal to the voltage gain A times V plus minus V minus. So this defines the primary characteristic of the op-amp. The output is an amplified version of the difference between the two inputs. Okay, a very simple Thevenin's equivalent model for the op-amp is this. So between V plus and V minus, if we look in, there is a resistance. There is no voltage source, Thevenin's voltage source looking into the op-amp. It is only a resistance. If we look into the output, and as I said, the output is measured with respect to ground, then we have output and ground. If we look in, we'll see a Thevenin's equivalent will be a Thevenin's voltage source in series with a resistance. The resistance is R out, which is very small, and the voltage source is A into V plus minus V minus. So it's a dependent source. Its value depends on these two voltages. All right. So now let's go back to the circuit. So here is the first circuit we look at. So this is our op-amp, and we are connecting R2 between the output and the negative input, R1 from the negative input to ground, and we are connecting an input voltage to the positive input terminal. I have called the current going into the op-amp as I in. So if we replace this op-amp with its Thevenin's equivalent, then we'll get from Vs, we'll get the input resistance to Va, and at the output, we'll get voltage source, the dependent voltage source. So this I have drawn with R out equal to 0. Alright, and as you, I hope, recognize, this is the same circuit we looked at 3 minutes ago. Alright, so this is the equivalent circuit for this simple op-amp circuit. And as we just saw 3 minutes ago, this circuit has two unknown voltages, VA and VO. And there are two equations. One is the KCL at VA, which I have not written here again because we just wrote it. And the equation at VO, which is VO equal to AVI, all this. We just saw this. So I am repeating because this is very important. Or Vs equal to approximately equal to Va. So as we just saw, an op-amp has a very large A, and therefore VO by A approximately 0 is a very reasonable assumption. So you think about this as 10 raised to 5. And VO is typically not more than 10 volts. So 10 divided by 10 raised to 5 is 10 raised to minus 4. So that is 0.1 millivolt. That is such a small voltage that it is okay to say that this voltage is basically 0. Or in other words, we say that suppose Vs is 1 volt, then Va will be different from Vs by 0.1 millivolt. So if this is 1, Va would be let us say 1.0001. So we say we don't care about that 0.0001, and these two are approximately equal. Okay. The point of this, the primary point of these equations is that if we look at this equation, we have two equations, two unknowns, Va and Vo, and we write a KCL at Va, and the other equation we theoretically write is this, Vo is equal to AVI. But the point of this is that instead of writing Vo equal to AVI, we could equivalently write Vs is approximately equal to Va. Alright, because A is large. So these equations show that this is equivalent to this. And this is critical in analyzing op-amp circuits. So with this, we make a statement. We say that, okay, this is valid. All these are valid only if there is something connected between the output and the negative input of the op-amp. We'll see this later. I'm not explaining this right now. Maybe by the end of this lecture, I'll tell you a little more about it. But for this to be valid, this is required, that there is a connection. Okay, so with that, let me make this statement. So whenever there is a direct or indirect, I'm sorry, this is or, direct or indirect connection between the output and the negative input node of the op-amp, one says that the op-amp has negative feedback. Okay, very important term. Whenever such a connection exists, one says that the op-amp has negative feedback. Okay, that is one. Number two, if Rin is very large, then we can say that In is approximately 0, because if Rin is large, then the current is small. So that is here. This is In. So if Ri is Rin, same thing. If Ri is very large, that means the current in Ri will be very small. Therefore, we say that, well, this current is basically, it's very small and basically 0. So we'll assume that In is 0. And we call the okay. So we'll call an op-amp ideal if it has an infinite voltage gain, an infinite input resistance, and a 0 output resistance. Okay, so in this circuit I have already made R out 0. So we'll say if Ri is infinite and if A is infinite, then we say this is an ideal op-amp. Real op-amps are close to ideal. They're not exactly ideal, but for most applications they can be assumed to be ideal. So this is the definition of an ideal op-amp. And for an ideal op-amp, we can assume that V plus is equal to V minus and In equal to 0. Okay. For an op-amp that has negative feedback, we can assume that V plus is equal to V minus and In is equal to 0. What are we saying? If this is ideal, then In is 0 because Rin is infinite. No current flows into the op-amp because Rin is infinite. We are saying that if A is infinite, this voltage is equal to this voltage. Vs is equal to Va in this circuit. Vs is basically the voltage at the positive terminal of the op-amp. Va is the voltage at the negative terminal. So these two voltages are basically equal for an ideal op-amp. Okay, with these assumptions, solving op-amp circuits becomes very simple, much simpler than it is possible without these assumptions. Okay, I'm sorry. Okay. So let's look at that circuit again. This is the same circuit I have drawn again. So now we say, okay, I'm going to make the assumption that no current flows into the op-amp. I'm also going to assume that this voltage is equal to this voltage. So if these two are equal, then we can say that V minus is equal to V in. V in is a known voltage, so we know now V minus is also equal to V in. We already know the voltage at V minus. Now we need to find VO. The purpose of, well, in all amplifier circuits, what we want to find is the output voltage as a function of the input voltage, because it's an amplifier. So the most important quantity is what is the ratio of V out to V in. So we say, okay, we know this voltage, we'll write a KCL at this node. So we say V minus by R1, the volt current here, plus V minus by minus VO by R2 is equal to 0. We solve this and we get VO equal to 1 plus R2 by R1 to V minus. V minus is equal to V in. So we get VO equal to 1 plus R2 by R1 into V in, which we already saw a few slides ago. But here, with all the assumption, the analysis becomes very simple. So this circuit is called a non-inverting amplifier because the output and input have the same sign. If the sign is negative here, it's called an inverting amplifier. Okay, so let us look at this expression. What this expression is telling us is that I can use this op-amp. By the way, op-amps are widely available in the market. They are simple chips and they are very cheap. They are one kind of a general purpose op-amp will cost about 5 rupees or so. And the op-amps are probably the most widely used chips in the whole world, in the terms of the number of chips that are produced, etc., etc. And of course, there are different types of op-amps with different characteristics. There are some which have a very large input resistance, some have a low output resistance, some have a very large voltage gain, some have all of it, and they have different frequency characteristics and speed characteristics, which we'll see later. So the advantage of op-amps is that I can buy an op-amp, a general purpose op-amp that has high R-in, has low output, low R-out and a high voltage gain, and then I can make an amplifier of whatever gain I want depending on the application I'm using it in, by simply connecting two resistors R2 and R1 across it. Alright, so the vast number of applications for which this chip can be used makes it very versatile. So there are applications where I may need a voltage gain of 2. I just put R2 by R1 equal to 2. And there are others when I need a gain of 10 or 20 or 100 or whatever. Anything I want, just to connect two resistors, and I have an amplifier I need. Otherwise, if I want to design an amplifier from scratch every time, it is a much more complicated process. And so this makes the design of amplifiers very trivial. So that is the beauty and usefulness of op-amps. Okay, so let's look at a couple of more op-amp circuits. So here is a circuit where the input is applied to R1. So here the input was applied to the positive terminal and the R1 was grounded. So here we are applying the input to R1 and the positive terminal is grounded. Now we make the same assumptions. We say the current going into the op-amp is 0. V minus is equal to V plus. V plus is 0, so V minus is 0. And then we write a KCL at this node. So we'll say, what have I written? V minus minus V in by R1 plus V minus minus VO by R2 is equal to 0. The same current flows in R1 and R2 because the current going into the op-amp is 0. So this current is equal to that current, and if we solve this, V minus is 0. So if we solve this, we get VO is equal to minus R2 by R1 into V in. So this is called an inverting amplifier because the output has a negative sign compared to the input. Why is the word inverting used? It inverts. It inverts because if you think of a sine wave, which is the most widely used signal in electronics. So V in is a sinusoidal signal, then VO will be negative of the sinusoidal. So when V in is going positive, VO will go negative. So it's kind of inverted across the x-axis. That is why the word inverting is used. All right. Okay, one very important thing. So in both these circuits, we wrote a KCL at this node. We did not write a KCL at this node. Right? Why did we not write a KCL at this node? So let's go back. I'm going to go back a couple of slides. Because inside the op-amp, VO is connected to a dependent voltage source, assuming that RO is 0. Rout is 0. If Rout is 0, we have this connected inside. So if we were to write a KCL at this node, we will not know the current in the dependent voltage source. We've seen this earlier. We do not know currents in dependent sources as a function of the voltage across it. The current in voltage sources is determined by the rest of the circuits. So one never ever writes a KCL at the output node in an op-amp circuit. Alright, never ever write. If you write, okay, if you write, then you have to write the current going into the op-amp as some current. And so the KCL at this node will be the current in R2 plus the current going into the op-amp equal to 0. But we don't know that current. So we've written one equation, but we added one additional unknown variable. So there is no point writing that equation. All right. So never ever write a KCL at the output node of an op-amp, because you don't know the current going into the op-amp or out of, whichever way it is. Okay, let's look at the next circuit. Let us look at this circuit. So we have connected the output to the negative input directly of the op-amp, basically shorted the two. And at the input, we have a voltage source, and that voltage source has some source resistance, 100 ohms, that's connected to the positive terminal. The question we ask is, how much is VO? It's actually the simplest of circuits, because we say that, well, this is an ideal op-amp, so the current going into the op-amp is 0, which means that there is no current in this 100 ohm resistor. So if this voltage is 1 volt, this voltage is also 1 volt, because there is no voltage across the 100 ohm. And if this is 1 volt, because V plus is equal to V minus, this is 1 volt, and 1 volt is connected to the output, so the output is equal to 1 volt. Or in general, if this is some V in, then VO is equal to V in. The output is equal to the input. This is called a unity gain amplifier. It has no gain. Gain is unity. The output is equal to the input. Alright, so the term used is unity gain buffer. We'll talk about buffer in just a minute. So the question is, well, if VO is equal to V in, why on earth do I need an amplifier to put in between VO and V in? I can just directly connect this wire to the output and not have the op-amp at all. What is the purpose? So let us look at the purpose. Let us see. Okay. Suppose at the output of this op-amp, I have connected a speaker. Alright, so let's say this is some audio signal coming from a microphone. Well, okay, let's say this is a signal coming from some source that has a series resistance, source resistance of 100 ohms. And I want to, so this is some audio signal. And the Thevenin's equivalent of that signal is the voltage source in series with a resistance. So now if I connect a speaker to this source, and as the speaker, as I have said before, has a Thevenin's resistance of 8 ohms. So let's say I didn't have an op-amp. I said, well, why do I need an op-amp? I don't want to use the op-amp, so I'm just going to connect directly the speaker across the voltage source, which is this 1 volt in series with 100 ohms, and this is 8 ohms. So now what is the voltage across the speaker? What is the voltage that the speaker sees that it is going to convert to sound? So this is 100 ohms, 8 ohms, so this is a simple voltage division. So we say Vx is equal to 8 divided by 100 plus 8 into 1 volt. Now that turns out to be 74 millivolts. Okay, so what happened? I wanted the 1 volt to drive the speaker, but because of the source resistance of the 1 volt, the actual voltage that appears across the speaker is only 74 millivolts. It is what? 7.5% of the voltage I wanted. This effect is called in electronic circuit as loading. When the speaker is called a load, and this is the source resistance. So when the load resistance is much smaller than the source resistance, then the output across the load is much smaller than the voltage that is applied to it through the source resistance. That effect is called loading. The load causes the output voltage to reduce. And this is not good, right? I wanted 1 volt, I get only 74 millivolts. That's not good. So now let's look at it here. So I say, okay, I have the source and the source resistance. I'll put an amplifier in between, and I'll connect the output of the amplifier to the speaker. Now what happens? This VO is 1 volt because of the op-amp. Even when I connect a speaker, this voltage does not change, assuming that the op-amp is ideal. So if the op-amp is ideal, then this VO is directly a voltage source, a dependent voltage source. And so dependent voltage source connected to an 8 ohm, it doesn't matter what we connect to it, the voltage does not change. And therefore we get a full 1 volt appearing across the speaker and avoiding the loading effect that occurs if we connect it directly. And this is the advantage of this unity gain stage. It does not provide gain, but what it does provide is the output with a very low output resistance. So Thevenin's resistance looking into the output of the op-amp, if it is ideally 0, then no loading occurs at the output. And this stage is called a buffer. So it buffers the input from the output and decouples the resistances, the source and load resistances. So this is a very important circuit in voltage amplification. Okay, let's look at one more circuit. This is called a summing amplifier. So we have 3 voltage sources connected to the negative input node through resistances R1, R2, R3 and a feedback resistance RF. Now I want you to pause and find VO in terms of V1, V2, V3, R1, R2, R3 and RF. One thing we know already is that V plus is equal to V minus, V plus is 0, so V minus is 0. So please pause the video and find VO in terms of all the other quantities. Okay, I'm continuing. So the answer you'll get, so what you'll do is you'll write just one KCL at this node, and I've written current going into the node as positive because that's easier. So you get V1 by R1, V2 by R2, V3 by R3 are the currents going in, equal to, okay, VO by RF is going in, so on the other side it's minus VO by RF. And so we'll get VO equal to minus RF into all this. If R1, R2, R3 are equal and they are equal to R, then this comes out and we'll get minus RF by R, V1 plus V2 plus V3. So this circuit sums the 3 voltages V1, V2, V3 and produces an output that is equal to the sum of the 3 voltages if the resistances are equal. If they are not equal, it produces what is called as a weighted sum. So the weighting of each voltage is determined by the resistances R1, R2, R3. Okay, so this is a summing amplifier. You can imagine a difference amplifier, an amplifier that will produce a difference between 2 voltages. I'm going to assign that as homework to you. So I'm not solving it here. It is quite straightforward. Okay, so this is the end of this lecture. We'll continue next time.